video, we are going to continue with what we did in class today. So today you were given some data, and in this case it was the decomposition of dinitrogen pentoxide over time. So you got data that showed you, as time progressed, how the concentration of N2O5 changed, right, as it decreased, as it was decomposing. All right, and so then what we did in class was we needed to figure out what was going to give us a straight line. What plot of that data would give us a straight line? Is it going to be concentration over time versus time? Not over time. Concentration versus time. Is it going to be the natural log of concentration versus time? Or is it the reciprocal of concentration versus time? Okay, so that's what we need to do when we're given integrated data, concentration and time, is we need to figure out what graph is going to give us the straight line, and that tells us then the order of that reactant. And so what we found was that this is a first order reactant. The natural log of the concentration versus time is what gave us a straight line. So that tells us dinitrogen pentoxide is a first order reactant. So now that we know that, okay, we need to determine the rate law, determine the integrated rate law, find the value of the rate constant K, and calculate N2O5 at 150 seconds. Okay. So, again, you guys, what we found was that plotting the natural log of N2O5 versus time, right, that gave us the straight line. So that tells us that this is a first order reactant. All right. So, determine the rate law. Okay, that's pretty easy. So let's write the rate law for this thing. It's going to simply be rate equals K times the concentration of N2O5, right? We're not going to write the 1 there, but we know it's a first order reactant. How do we know it's a first order reactant? Because the natural log of the concentration versus time is what gave us a straight line. All right. So this is where the linear relationship occurs. Natural log of the concentration versus time. Okay, so our rate law is this. Rate equals K times concentration of N2O5. Integrated rate law. Now, where are you going to find how to write an integrated rate law for this? Well, this is going to come from your rate law table that I had you copy into your notes. So the integrated rate law for this is going to be the natural log of N2O5 is equal to negative K T, which is time, plus the concentration of N2O5 naught, little 0. Okay, notice you guys, so I'm going to write this down. This is the rate law. Okay, this is the integrated rate law. What does this little 0 mean? This means at t equals 0, time equals 0. Now, this is actually in slope-intercept form. Y equals mx plus b. Slope is equal to negative k, the slope of this line. B is what? The y-intercept, the concentration at time 0. Time 0, there's the y-intercept, concentration at time 0. Okay, so all of them, you guys, all three of the integrated rate laws are in slope-intercept form. Y equals mx plus b. This being the slope of the line, m. All right, you guys, so the next thing that we need to do is we need to determine the value of the rate constant k. Okay, so the value of k. That's what we're trying to find. And because this is first order, you guys, the slope of the line is equal to negative k. Y equals mx plus b. Okay, so the slope of the line is equal to the opposite of k. So what we're going to do, you guys, is we are going to find the slope of our straight line, and that will be the opposite of k. All right, so how do we find slope? How do we always find slope? It is change in y over change in x. There's nothing new about it. So change in y over change in x, right? The rise over the run. Now, you guys, we have to use what gave us, the data that gave us the straight line. So, in this case, it's going to be the change in the natural log of N2O5 over the change in time. Right? Because the natural log of the concentration is what gave us the straight line. We certainly can't just plug in concentration here. It has to be the natural log of concentration. All right. And so what I'm going to do is I am going to take the last data point, which is negative 5.075, minus the first data point, 2.303, and that's going to be 400, so right, time at 400 minus initial time. All right, and in general, you guys, that's what you want to do. You want to use your first and your last data set here. All right, and so what do we find? What's the answer to this? If you do this math, you should end up getting here negative 2.772 over 400, and that is equal to, do this division, negative 6.93 times 10 to the minus third. Okay, now, is that equal to k? No. This, right, this is the slope of the line, so this is equal to the opposite of k. So what is the value of k? K going to be equal to 6.93 times 10 to the minus third. And our unit is seconds to the negative 1. The last thing that we need to do. The last thing that we need to do is we need to calculate the concentration of N2O5 at 150 seconds. All right, you guys. Now we have the value of K. And what we're going to do is we're going to plug into the integrated rate law. Our time is going to be 150 seconds. We know our initial concentration of N2O5. We know the value of K. And so we are going to be able to calculate what the concentration at that time is going to be. So at the top, you guys here, I'm just going to write it again, just so I can keep referring back to it. Well, we're trying to find this at a time of 150 seconds. So I'm going to say the natural log of N2O5 is equal to negative. My value for K is 6.93 times 10 to the minus third. It's the opposite of this product, times 150 seconds plus my initial concentration, and my initial concentration is 0.1 molar. So it's going to be the natural log of 0.100 molar. Okay. Now, the product of this with its opposite, and I hope that you would do it on the calculator at home, is going to be negative 1.040. You should try this and make sure that this is what you get. Minus 2.303. Because the natural log of 0.100 is negative 2.303. Okay, so that's why I just made it minus 2.303. All right. So we end up having the natural log of the concentration that we're looking for is equal to negative 3.34. So again, I am looking for this concentration at 150 seconds. Okay, so I'm going to put the time that I'm looking for that concentration. I have calculated my value for K. This is my initial concentration. Okay, so now I'm here. So this is the natural log of the concentration. This isn't the concentration. And so how do I convert? This is the natural log of it. I don't want the natural log of it. I just want this. So what do I do? Well, I have to find the anti-log of negative 3.343. And so what we do then, N2O5. Now, in my day, we called it the anti-log. What button do you push on your calculator? E to the X. And that's how you find an anti-log. Right? That'll get rid of your natural log here. Okay, and so that tells us then, you guys, that the concentration of N2O5 at time 150 seconds is 0.0